Okay, good morning, everyone. Let's pick up on chapter 2. And let's go to our relevant section, section 02. Okay, so I had introduced the topic of semiconductors, typical elements and the materials that we use. But I want to do a quick note and a recap about this. It's part of the homework. There are a couple of questions about calculating resistance. And this equation right here is what you would need to use to calculate that resistance. Okay. I hope everybody saw the or read the announcement about the homework, right? So typically I will use announcements to communicate with students. Okay. Sometimes I might use email, but typically it will just be posted as an announcement. So if your notification settings are off, you might want to turn them on, at least for announcements. You can go into Canvas notification settings and you can control what alerts you receive. Okay. So specifically, again, I'm specifying and emphasizing that I will always post an announcement. So if you don't receive an email, make sure your notification settings in Canvas are on. So resistivity is rho, resistance is rho L over A. Couple of problems in the, actually one problem in the homework assignment, where you take the length and the cross-sectional area of that piece of material and you calculate the resistance. Straightforward, plug and play. If you have any questions, let me know. All right. Okay, so this table lists the most common semiconductors that we use, columns 2 through 6. And the most common ones are right here, column 4, silicon and germanium. Germanium actually was the first semiconductor material. But silicon overtook germanium as the de facto choice for, for its superior material properties. Okay, so silicon quickly overtook germanium, and almost every semiconductor device we use nowadays is based on silicon. Single element semiconductors are known as elemental or intrinsic semiconductors. And so those would be silicon and germanium. Okay. And they are from the column 4 of the periodic table. So they have 4 electrons in their outermost orbit, right? However, not every element that has 4 electrons in the outermost orbit is a semiconductor, right? Carbon is not. It actually is the opposite. It's an excellent insulator. And we'll talk about that in the next few slides. So single element semiconductors are known as elemental or intrinsic semiconductors. 2 or more are known as compound semiconductors. Okay, 2 or more are compound semiconductors. And examples would be elements from column 3 combined with elements from column 5. So we have gallium arsenide, gallium nitride. We have indium phosphide. And then let's see, cadmium sulfide, CDS. I believe I've also seen cadmium telluride. Okay. So you combine elements from two different two different columns of the periodic table, you get what is known as a compound semiconductor. 3, 5, 2, 6 Gallium arsenide, gallium nitride, indium phosphide. There are 3,5 compounds. Cadmium and selenium, or cadmium sulfide is 2,6, and so is indium phosphide. Each one of those has a specific purpose. Gallium nitride is used for high frequency applications. It's like become a marketing keyword in modern day electronic chargers, right? If you've heard, okay, I have some brand new gallium nitride charger on the market, charges at like 90 watts, blah, blah, blah. But that's what it's referring to. The semiconductor material inside it, probably like a small piece on the circuit board, is made of gallium nitride. Let's see. Gallium arsenide is used to make LEDs because it dissipates energy in the form of light. And then, of course, as I stated, there's a specific purpose and application for each one of these materials. But silicon is by far the most common one. Okay. Now, silicon, germanium, carbon, they all have 4 atoms in their outermost shell. So let's take a look at the atomic structure. Okay. In the early 1900s, Niels Bohr modified the prevailing model of an atom, right? Prevailing model of an atom was the Rutherford model. He modified it and created his own model, postulated the theory. And this has by far been the most common model in use for the last, I would say, almost a century. Okay. There was Schrodinger's model that came after, which is the more accurate way of presenting. But whenever we start talking about atoms, we always go first to the Bohr's model. Rutherford model was basically what Rutherford did was he had a very thin gold sheet and he fired positively charged particles on that gold sheet. And he discovered that most of the particles just passed through. Some of them were deflected at an angle, but most of them just passed through. So he postulated this theory that the atom is mostly empty space. Okay, so you have electrons orbiting a nucleus, but for the most part, it's an empty space. Hence, the charged particles were able to just pass through. And then Niels Bohr took Rutherford's model and postulated that the electrons are not just moving around the atom in a random sequence. They have discrete and quantized energy levels. Okay, they're fixed, they are rotating, or they're moving around the nucleus in a fixed orbit, not just a random energy level. And every orbit has a specific energy level. Okay, so orbits have specific energy levels. The outermost orbit is known as the valence orbit, the valence shell, and the electrons occupying that orbit are known as the valence electrons. And so column 4 elements, like silicon and germanium, have 4 electrons in their outermost orbit. Right? So far, so good. Now, this is not silicon. This is just random. It has 5 electrons in the outermost orbit. It's not silicon. Okay, so each orbit has a specific energy level. In general, the theory postulates that the smaller the orbit, the lower the level of the energy. The larger the orbit, the higher the level of the energy of the electrons. Okay, so smaller orbits, lower energy. And larger orbits, higher energy. Electrons are free to move depending on how much energy they have. They can move from a lower orbit to a higher orbit. And we are talking about a higher energy level, and we are talking about just the outermost, okay? Most of the electrical conduction is with the electrons in the outermost shell. The innermost shells, the inner shells are bound to the nuclei more closely, okay? So they are not participating in electrical conduction. Most of it is just the outermost shells. So electrons can actually jump from a lower energy level to a higher energy level. Okay, so it acquires energy, whether due to heat or light or due to an external applied field. It can acquire energy to jump up a level, or if it comes down from a higher energy level to a lower level, then it dissipates that energy in the form of heat or light. Okay. Now in silicon and germanium, of course, we have 4 electrons in the outermost orbit. And so when we look at the atomic structure of a silicon material, we see that these atoms share electrons to form a bond and a stable unit. Okay. Each silicon atom, and this is there on the next page also, but I'm going to draw it out here since I'm talking about it. Each silicon atom will share one of its 4 electrons with 4 neighboring atoms. Okay, so this atom in the center is sharing 1 electron with each neighboring atom, and those atoms in turn share 1 electron each. And so thus they form a stable outer shell with 8 electrons. Okay. When all of this is something I assume you studied in physics, chemistry previously, right? So we won't go too much in depth. Okay. So each silicon atom shares 1 electron each with 4 neighboring atoms, and they are in turn also sharing 1 atom each with that electron. So as an example, you have 1 electron here, and that 1 electron is surrounded by 4 neighboring atoms. It has 4 electrons in its outermost orbit shared with 1 atom each. And so they each have 8 electrons in their outermost shell. They form a nice stable unit. And the bond between the electrons and the atoms is known as a covalent bond. It's a covalent bond. Right here is an image of a silicon lattice unit cell. If you look at the structure of that unit cell, is sort of a diamond. Hence, it is also known as a diamond, tetrahedral diamond-shaped unit cell. Okay, it has nothing to do with the material diamond. Just the shape of the cell is diamond-shaped. Okay, just to be clear. More technically accurate would be tetrahedral. And then here, of course, is a close-up of one of the corners. You see 1 atom in the center sharing 4 electrons with its 4 neighbors. Okay, 4 neighbors. So far, so good. Any questions? Any questions at all? Okay. So when you have this kind of structure in a material, and the structure is repeated throughout the entire material, so it has regular periodicity, and it has a ordered structure throughout the entire material, we say that the material is crystalline. Here we say that the material is crystalline. So again, we have this atom. This atom is sharing its electrons with 4 neighboring atoms, and it creates a lattice structure that looks like this. Now, this is a 2-dimensional representation of a 3-dimensional structure. That's not as simple as this, but again, for explanation purposes, it suffices. You have silicon atoms, and 2 electrons each are shared on each side, 1 by each atom. Okay. So if it's an ordered segment with ordered segment, completely ordered segment inside the material, we call that material as crystalline. We also call it as, or refer to it as, single crystal. There is one same structure that is repeated continuously over the entire material. Okay. Single crystal solids or single crystal material have superior electrical properties compared to any other kind of material. Okay. If you have a unit cell, it has certain properties. If that same structure is repeated at regular intervals all the way through the structure, that means that you could create a device at one point and at a far point, and they would have very similar electrical properties. Okay, so all semiconductor devices are created with single crystal material. Well, most of them. We do have polycrystalline materials. There is use for polycrystalline silicon. Okay, but for the most part, we always begin with a single crystal material. So again, it has a ordered structure throughout the entire material. It has superior properties compared to any other structure. Polycrystalline material is ordered segments within a material. Polycrystalline, by its very name, tells us there are multiple crystals in that same material. Right? Poly is multiple. And so as an example, actually single crystal example would be something like this. Then I'll do polycrystalline. Just drawing this at random doesn't really make any difference. So crystalline, that structure is repeated, has the same structure throughout the material. In polycrystalline, you have ordered segments, but there's a break and it's not quite fully crystalline. Okay, so ordered segments within a crystalline material. So the structure is repeated, but not quite single crystal. And amorphous has no ordered structure whatsoever. Okay, amorphous has no ordered structure. And, and this is not just specific to like silicon or semiconductors. Any material applies to any material. Okay. As an example, what are diamonds made of? Carbon, right? Graphite, exactly the same thing, carbon. It's the structure of the bonding of the carbon atoms that creates different material, right? So you have amorphous carbon, graphite, carbon under tremendous pressure and very high temperatures creates diamond. That is how lab-grown diamonds are created. You have a vacuum chamber, you pass a gas through the chamber, which has carbon as an element. The gas decomposes. Whatever is not required is removed from the chamber. Carbon is left. And depending on the chemistry, of course, depending on the temperature and the pressure, that carbon forms and deposits as diamond on top of a seed material. And you run that for days at a time, run more and more gas over a continuous period of several days, and you now have a diamond film, a chemical vapor deposition. That's something that several of my peer grad students were actually doing when I was a grad student. I actually did work when I first began my research as a grad student. I was working with diamond thin films on silicon wafer. I still should have that sample somewhere in my office, but I just need to dig it up in one of the boxes. So if I find it, I'll bring it to class. Anyway, that's basically, the difference between amorphous, single crystal, and polycrystalline materials. When we have this kind of bond between, covalent bonds, they occupy certain energy levels. Okay, they occupy certain energy levels. So from there, we introduce a topic known as the energy band diagram or the energy band structure. Okay, we have the valence band, right? When you bring discrete atoms together and the electrons are shared, those electrons which are occupying a certain energy level, and this electron occupies another certain energy level, you bring them together, they now create a band of energy. So each atom is sharing one electron with its four neighboring atoms, right? So it has 4 electrons and it has at least one shared electron. So at a minimum, I would say there would be, let's say, 5 electrons or 5 energy levels. It probably is closer to 8. Okay. And this creates a band of energy that those electrons occupy. Okay. So this is a 2-dimensional representation of the energy bands. There's no axis as such. It is simply referring to the energy levels in a atomic structure. Okay. It's known as the energy band diagram. So these arrows are pointing up. Energy increases as we go up in this diagram. So we have the energy bands of the outermost shell of these electrons. They occupy a level that is known as the valence energy band. Okay, they have valence energy. Now, let's look at the right. Let's look at the right. You have the valence band, the energy level of a valence band, and then you have the conduction band, where the electrons have acquired enough energy to be able to freely move around the material. Okay. Electrons, when they have sufficient energy to freely move around a material. And that is known as the conduction band energy. Okay. So if a material has overlapping conduction bands and valence bands, meaning there are several million electrons that have acquired sufficient energy to freely move around a material, we refer to that material as a conductor. So there are always free electrons available to conduct electricity. Okay, that's what it means. So we have valence band electrons with valence energy levels, and then you have conduction energy levels, where the electrons have acquired sufficient energy to freely move around the material. Okay, so they're not part of any atomic structure. They're free to move around the material. And hence that material is termed as a conductor because it is a good conductor of electricity. Let's take a 10-second pause. Let me know if you have any questions. Yes. Okay, so the question being asked is, what's the difference between valence and conduction? So valence bands, or the electrons in the outermost orbit, which is basically referred to as the valence band, so valence electrons, they have energy levels, but they are part of the covalent bond. Okay, so they are part of the atomic structure right here. Okay, so these electrons that are shared and are part of the covalent bond, they are being shared between the atoms. If they acquire enough energy, they move out of these, they break these bonds and they move out of their position in the lattice, which is actually coming on in the next slide. So I'll fully answer your question in the next slide right here. Okay, a couple of slides. But conduction essentially means that the electrons have broken the covalent bond and they now have acquired sufficient energy that they can freely move around the lattice, and so they're free to conduct electricity. Coming back to this diagram, on the left, the valence band energy and the conduction band energy are far apart. Okay, they're far apart. The electrons can never acquire enough energy to be able to freely move around the material. And hence that material is termed as an insulator. Okay. So the gap between the two is referred to as the forbidden. So it's a forbidden gap or a forbidden band. Again, these energy levels form a band, and so we refer to them as valence band, conduction band, and the forbidden band. Oh, by the way, everything that you learn in this chapter is highly condensed. Okay. This chapter 2 is an entire course by itself. EE 524, solid state electronics. Yes. Okay, so the question being asked is if the forbidden gap is similar to the infinite well. Different models, but yes, it makes sense. Kind of. Yeah. But we are looking at it from the perspective of whether this material can conduct electricity or not. Okay, that is what we are interested in. So we have conductors on one side, right? We have conductors on one side, and you have insulators on the other side. In conductors, the electrons have acquired enough energy. Well, actually, they already have enough energy that they're free to move around. Okay, so there's sufficient number of electrons that are always free to move around. In insulators, there are not many electrons that are free to move around, and they cannot acquire enough energy to be able to cross into the conduction band. Okay, when I state cross over to the conduction band, it means they cannot break the covalent bonds. Yes. So the question being asked is whether the conduction band is another discrete level. The answer is yes. Yep. But in 2 slides, we will see that the conduction band also means that the electrons can break free from its covalent bond. But essentially, that's what it means. Yeah. All right. Any other questions? Okay. So right in the middle is what we have, what we call as semiconductors. We have a band gap. We have a forbidden gap in there, but the electrons can acquire enough energy to jump over from the valence band to the conduction band, meaning they are able to break free of their bonds. Okay, they are able to break free of their bonds. The levels of the energy are noted as EV. EV is for the highest level of energy in the valence band. EC is the lowest level of energy in the conduction band. And the energy band gap is defined as EG. Okay, the band gap energy is defined as EG. And simply stated, of course, EC is at a higher level than EV. And so EG is the energy that is required to breach that gap. Yes. Thermal or light. And it's a good question. So how does that energy come about? It's either heat or light, or an external applied electric field also. That's coming up in the next couple of slides. And EG, like resistivity, is a material property. Okay. The material property in electron volts, specify electron volts. And you can see silicon and germanium right here, 0.66 and 1.12. Germanium actually has a lower band gap energy required than silicon. So in some respects, germanium is a better conductor, but silicon has many other advantages over any other element or any other intrinsic semiconductor. One of the biggest advantages silicon has is, of course, it is the second most abundant element on this planet. It is not available in pure form, but is mostly part of other compounds like silicates, sand, dust, right? We purify it from those, from those raw materials, but is the second most abundant element in the Earth's crust. Okay. Also, another reason is silicon, when oxidized, creates a very good thermal and electrical insulator. So an oxide of silicon, silicon dioxide, which is SiO2, is a very excellent electrical insulator and a thermal insulator. Germanium, not so much. Silicon dioxide is also known as glass. Glass is silicate, silicon dioxide. So it has excellent electrical properties, transparent, and it's very easy to grow. It's like baking cookies. You take a silicon wafer, you stick it in an oven, and you heat it up to 1,000 degrees C. Except for the difference in temperature, it's like baking cookies. Anyway, so SiO2, that's one of the big reasons why it's an excellent choice for semiconductor applications. When you're trying to create a microchip conducting devices, you want to isolate them with insulating material. And so if you can just create and grow SiO2 easily, well, that makes the job very easy. Take a look at carbon, 5.47 electron volts. The gap is so large that it cannot be breached just by normal material, normal application of an electric field. Okay, just at room temperature, carbon is not a semiconductor in the normal sense. Okay, so the gap is large enough that we do not use it as a intrinsic semiconductor because the electrons by themselves do not have sufficient energy to cross over into the conduction band. There are semiconductor materials created using silicon by combining silicon and germanium. So you have silicon germanium material. You also have silicon carbide. So you can create silicon carbide material that can be used. But carbon by itself, not so much. And then tin, as you see here, very small energy gap. For me, I personally just refer to all metals and conductors as having zero energy gap. In real life, of course, everything is never zero. There's always a small number attached to it. Copper by far is the smallest gap, so it's an excellent conductor of electricity. Gold, again, has a very small gap. Gold is by far the best conductor of electricity. Okay, does not degrade, does not create any oxide or rust. So there are applications where we do use gold as an electrical conductor. Anyway, coming back to the lattice structure. We start at absolute zero. Okay, any material at absolute zero is, by the way, the temperature in Kelvin, 0 Kelvin, named after Lord Kelvin. He invented that scale. And it is minus 273 degrees C. Okay, minus 270 degrees C. Absolute zero. It's so cold, I can't freaking think, move, or do anything. Okay. At absolute zero, if you have a semiconductor material, let's say silicon lattice, for example, all of the electrons are in shared covalent bonds. Okay. They are all occupying all of these states right here. And this is where you'll get the answer to your question, or the full answer to your question. They are all occupying these states in the silicon lattice. They are not moving around anywhere. Okay, so absolute zero, all the electrons are below EV level, valence energy level, below EV. The theory states there's not a single electron that has enough energy to conduct. So none of them have EC levels. As the temperature rises above 0 Kelvin, some electrons acquire enough energy to free themselves off the covalent bond, and their energy level is now higher than EV. And so they jump from the EV level to the EC level. They break their bond right here, and they are free to move around the lattice structure. They are not part of any atom. Okay. In a covalent bond, you have, let's say again, silicon. In a covalent bond, you have 4 electrons shared equally amongst 5 atoms, right? So the forces of attraction and repulsion among the electrons themselves and the nuclei of the surrounding atoms is equal. They are not pulled or shared in any other direction because it's all equal. Okay, so when they acquire enough energy, this is from thermal energy. From absolute zero, you're rising above, so it's acquiring thermal energy. Those electrons acquire the energy level to move from EV to EC. Their energy level has now changed from EV to EC. That energy is sufficient to break that covalent bond, and they are now free to move around the crystal structure. They are not part of any atom. And once an electron moves out, it leaves behind an ion. Right? Electron moves out, leaves behind one extra positive charge. Overall, the charge is neutral, because the electron is not just, it's left its spot, it's left its seat, but it does not exit the room. Make sense? Right? So it's free to move around the structure, but it's not left. So the charge, the total charge is still neutral in that structure. This is important to remember, because when we add impurities to this material, that's going to be different. We have extra positive charges and then extra negative charges. But just because the electron moved out, the overall charge in here is completely neutral. And this also leads us into actually, before I get to that, let me just refer to this. Room temperature is typically referred to as 25 degrees C, or in this case, 300 Kelvin, which is equal to 27 degrees C. Just as a reminder, the Kelvin scale is linear. Okay, you simply add. If you have degree C, you simply add 273 or subtract 273. Okay, so at room temperature, 27 degrees C, there are several thousand millions of electrons in a structure that have acquired sufficient energy to break free and climb from the valence level EV energy level to EC. But that number is far lower than what is available in a typical conductor. So the number of free electrons is far lower than what is available in a conductor. So it's not quite a conductor, hence the term semiconductor. Make sense? And does that fully answer your question from before? Kind of? Okay. All right, let's take a longer pause to think over all of that. Let me know if you have any questions. As I stated, what we are learning in this chapter is highly condensed. There's a whole lot more to this. Fills entire books. It is an entire course by itself if you wish to take it. Device physics, EE 524, solid state electronics. Any questions? Yes. What is like semiconductor material actually provides over like conductor material? Like, I guess that's actually a very good question. So the question being asked is, what advantages do semiconductors have over conductors? And the biggest advantage is we can control everything about semiconductors. Conductors, of course, if you want to create a simple conductor, yes, we create a wire, we use conducting material. But a semiconductor material, we can add some material to the semiconductor, we can control the resistance, we can control how much current or how many electrons are available. And so we can control the flow of current, we can control the voltages at the input and the output. And that's the biggest advantage. It's, yeah, exactly. It's like a slider we can adjust. So depending on the application, we can add more material to the semiconductor to make it a resistor, or we can make it a pure conductor. But the important thing is control. We can control what that material does. And that's the advantage of semiconductors over conductors. Any other questions? Yes. So what's the question being asked is, what stops the insulator from jumping the forbidden gap? The gap is so large that energy cannot overcome. But you can, but the element will just, I don't know. If we have wood and we apply energy to it, I don't expect it to have I don't expect it to have enough energy to jump over. Physical limits, laws of nature. Theoretically, we would think it would be possible to supply enough energy, but practically not so much. It would probably, there would be so much thermal energy generated that would just like blow up or start a fire. Everything we talk about or we speak about here has physical laws that constrain the operation of devices and the material. Okay, so theoretically speaking, yeah, we would think, why can't we provide enough energy for it to for an insulator to become a conductor? Theoretically, yeah, it's possible. Practically, impossible. But good question. Two more things. First is a concept. First is a concept of a particle that is created when an electron moves out of its spot. When an electron breaks its bond and moves out of its spot, it leaves behind an empty spot. That empty spot is known as a hole. Okay. And it's important to understand this concept because let's say you have these spots inside a lattice structure. You have an electron that moves from one spot to the next. Every time an electron moves from one spot or becomes free of the covalent bond, it leaves behind an empty spot. That empty spot is treated as a particle by itself. That particle is known as a hole. So similar to electrons, we treat that as a particle by itself. And the particle is labeled as a hole, and it has a positive charge. Electrons have negative charge, and holes have positive charge. Going forward, we have to think of hole as an independent particle, similar to electrons. Physically speaking, it's not a particle itself, but for the entirety of your career as an electrical engineer, you'll have to get into the habit of referring to hole as a particle by itself. We have electrons with negative charge and holes with positive charge. Okay. So every time electron moves out, it leaves behind an empty spot, positively charged particle called hole. And then last, I want to refer to this equation. It's one of the questions also in the homework that I think it's already in homework 3 or maybe it's upcoming. But anyway, so the number of electrons that are free to move around the material is given by this equation right here. Ni squared. The N, so the N is for the number of electrons or number of carriers to be exact. Number of carriers, and I is for intrinsic. So you have these carriers that are present in that crystal structure due to thermal energy, also due to light. Okay, light and thermal energy is acquired by these electrons. They jump the state from valence to conduction. Okay, so at room temperature, there are sufficient number of electrons or carriers that are free to move around the crystal structure, and that is given by this equation. This equation has a few terms. Eg and K are constants, right? Eg and K are constants. Then we have temperature in Kelvin, which would be given to you. B is also a constant. It's a material dependent parameter that defines the mobility and the thermal conductivity of the lattice structure. Okay, so that is also a given. And then simply plug into this equation. Okay, so depending on the temperature, the number of electrons, the number of free carriers in a structure changes, and that is defined by this equation. Okay. So we'll end class here today, and we'll pick up here again on Friday. In the meantime, it goes without saying, but I'm going to state it now. You have access to the book. Everything that I'm doing is from the book. I am not trying to deviate from the department mandated books. Okay. So Jaeger is the book that we are using for these chapters. Chapter 1 correlates to chapter 1 in the book. Chapter 2 here relates to chapter 2 in the book. So every time I cover a topic, please open the book, read about the relevant sections. You have it available via Connect, And then again, if you have any questions, reach out to me. All right, let's end the recording.